Have you ever stopped to think about what actually keeps our lights on? I mean, really think about it. There's a secret language, a high-speed code of numbers that's constantly working behind the scenes to protect our entire electrical world. And today, we're going to learn how to speak it.
So here's our game plan. First, we'll look at the mystery of these numbers. Then we'll figure out why they even exist. After that, we'll get into the fun part, decoding the most common ones you'll see. Then we'll take what we've learned and apply it to a real diagram and wrap it all up with a new appreciation for these silent heroes of the grid.
All right, let's dive right in with the puzzle itself.
I mean, if you've ever seen an electrical one-line diagram, you know exactly what I'm talking about, right? It's this web of lines and symbols, and sprinkled all over are these numbers that just seem totally random. What on earth are they trying to tell us?
Okay, look at this. You see those numbers? 50, 51, 87, 52? They're not just there for decoration. Each one tells a very specific story about how this system is protected. Right now, it might look like hieroglyphics, but trust me, by the time we're done here, you're going to be able to read this thing no problem.
So you might be asking, why even have a code? Why not just write out, this device protects against high current? Well, the answer comes down to the incredible scale and, more importantly, the speed of our power grid.
You have to remember, our grid is this gigantic, interconnected machine. When something goes wrong, say a tree falls on a power line, that fault has to be found and cut off from the rest of the system in, like, the blink of an eye. We're talking milliseconds. Otherwise, you get a cascading failure. So we absolutely need a standardized, universal language that every engineer, every operator, and every piece of equipment can understand instantly.
And this is it. This is the solution, the ANSI/IEEE standard. Think of it as the official decoder ring for the entire power industry. It assigns a specific number to every type of protective function so that anyone, anywhere in the world, can look at a diagram and know exactly what's going on. It's our Rosetta Stone.
Okay, this is the fun part. Let's actually start cracking the code and look at some of the most common and critical numbers you're going to run into out in the field.
First up, let's talk about the overcurrent family, devices 50 and 51. These are probably the most common types of protection you'll see. Think of them as the grid's smoke detectors, constantly sniffing for dangerously high levels of electrical current. Now, the difference between these two is all about timing. Device 50 is what we call the fast guard. If it sees a massive, undeniable spike in current, like a direct short circuit, it acts instantly. No delay, no questions asked. Boom. But device 51, that's our patient guard. It sees a high current, but it's programmed to wait for just a moment. Why? Well, sometimes you get temporary high currents that are perfectly normal, like when a big motor starts up. The 51 waits to make sure it's a real, sustained problem before it sounds the alarm.
So if the 50 and 51 relays are the detectives that spot the problem and sound the alarm, who's the one that actually kicks down the door? Well, that would be device 52.
Device 52 is the AC circuit breaker. This is the muscle of the whole operation. The relays, like 50 and 51, they're the brains. They do the detecting. But it's the 52 breaker that gets the signal and then physically, mechanically opens the circuit to stop the flow of that dangerous current. It's what isolates the problem from the rest of the healthy system.
But hey, protection isn't just about watching the current. It's also about voltage. So let's meet another critical pair of guardians, devices 27 and 59.
This one's pretty straightforward, but it's super important. They're basically two sides of the same coin. Device 27 is the under-voltage relay. It keeps an eye out for when the voltage sags too low. Think of a brownout, which can really damage sensitive equipment. And device 59 does the exact opposite. It protects against overvoltage, those dangerous spikes and surges that can literally fry your electronics. They keep the voltage in that safe Goldilocks zone.
All right, now for one of the most ingenious, most clever protectors in the whole system. Let's talk about the differential relay, device 87. This one is just brilliant. An 87 relay is usually used to protect one specific, very expensive piece of equipment, like a huge power transformer. What it does is it measures all the current going into the transformer and all the current coming out of it. In a healthy system, those two numbers should be basically identical, right? What goes in must come out. But if they're different, that means current is leaking somewhere inside the transformer itself, which is a very, very bad thing. It's an incredibly sensitive and fast way to detect an internal fault.
So, with everything we've just learned, let's go back to that confusing diagram from the beginning. Because it's not a secret code anymore, is it? It's a story about protection.
Okay, let's put it all together. See the transformer there in the middle?
That 87 differential relay, that's its personal bodyguard, just watching for any internal problems. Then, on the power lines connected to it, we've got our trusty 50 and 51 overcurrent relays standing guard. Now, if any of those relays, the 87, the 50, or the 51, sees a problem, what do? They all send a trip signal to the 52 circuit breaker, telling it to open up and safely cut the power. See? It's a coordinated defense, and now you can actually read it.
Now that we can read the language, let's just zoom out for a second and appreciate the bigger picture and why this all matters so much.
You know, this official definition from the IEEE really just nails it. The job of a relay isn't to stop bad things from happening. Its job is to detect those abnormal or dangerous conditions and then initiate action. It's all about damage control, about minimizing the impact of a fault and keeping the rest of the lights on.
So what we've really been decoding today isn't just a technical standard. It's the language of a silent, high-speed symphony. Each number represents a musician, a protective device, all playing its part in perfect coordination to keep our modern world powered, reliable, and safe. It's pretty amazing when you think about it.
So I'll leave you with this thought. The next time you're at home and the lights flicker for just a second and then pop right back on, don't think of it as a problem, think of it as a success story. Because in that split second, a silent conversation between a 51, maybe an 87, and a 52 just took place. They found a problem, they isolated it, and they kept your world running. And now, you know exactly what they were saying.